December 7th, 1941. Pearl Harbor burns, and within 72 hours, the United States military faces a logistics nightmare that has absolutely nothing to do with sinking battleships or burning aircraft carriers. Across the entire Pacific theater, from the sweltering jungles of the Philippines to the windswept coral of Wake Island, American forces are sleeping in canvas tents that disintegrate under tropical downpours within 3 weeks. The War Department's morning briefings turn grim when field reports start arriving, describing entire supply depots flooded, ammunition ruined, and soldiers hospitalized with pneumonia because their shelter literally fell apart during monsoon season. Traditional wooden barracks require skilled carpenters, weeks of construction. Time and lumber that simply does not exist on remote coral atolls scattered across thousands of miles of hostile ocean. The Navy runs the calculations and arrives at a terrifying conclusion. It would take 18 months to build conventional housing for the forces they need to deploy immediately. 18 months while Japanese forces consolidate their gains and American troops rot in the rain. In Washington, Brigadier General Eugene Raybould stands before a crisis table covered in weather maps and construction timelines that all deliver the same impossible message. His engineers present what they are calling the impossible equation, a problem that keeps the entire command staff awake at night. They need structures that can be manufactured in Pennsylvania, shipped 10,000 miles through submarine-infested waters, assembled by exhausted Marines who have never held a wrench in their lives and survive everything the Pacific can throw at them. And what exactly can the Pacific throw at you? 130-degree heat that melts tar, warps wood, and turns steel into branding irons. Category 5, typhoons with winds exceeding 150 miles per hour that tear conventional buildings to splinters and send debris flying like shrapnel. Monsoons that dump 15 inches of rain in 6 hours, transforming entire military bases into disease-breeding swamps. Oh, and the very real possibility of Japanese bombing runs turning your shelter into a metal coffin while you sleep inside. The brutal mathematics of the situation allow for no optimism whatsoever. A standard army tent costs $12, but lasts exactly 1 month in jungle conditions before becoming unusable rotting canvas. A wooden barracks building costs $8,000 and requires a skilled construction crew working for 6 weeks, assuming you can even find carpenters willing to work in a combat zone. Neither option works when you are island hopping across the Pacific and need immediate shelter for 50,000 men. But the British have been fighting this war longer, and their experience in North Africa offers a tantalizing glimpse of a possible solution. Since 1916, they have deployed Nissen huts, semicircular steel shelters invented by Canadian engineer Peter Nissen during the First World War. These corrugated iron half-cylinders house 30 soldiers, require no skilled labor to erect, and laugh at the sandstorms that bury everything else in the Libyan desert. On paper, they sound like exactly what the American military desperately needs right now. But paper specifications and Pacific reality operate in completely different universes, and the Nissen design carries critical flaws that would doom it the moment it encounters tropical deployment conditions. The British version uses heavy steel panels that need specialized lifting equipment, the kind of machinery that simply does not exist on a coral atoll under artillery fire. The ventilation system works brilliantly in the North African desert, where temperatures drop at night and humidity remains manageable. In Philippine jungle humidity, that same design transforms the interior into a steam cooker that hospitalizes men faster than enemy bullets. Most damaging of all, each hut requires custom foundation work, which means pouring concrete or constructing wooden platforms before assembly can even begin. That brings you right back to the carpenter problem, the skilled labor shortage, and the construction timeline that defeats the entire purpose. You cannot pour concrete foundations when Japanese forces are shelling your position. You cannot wait weeks for materials to arrive when your troops are sleeping in contaminated mud. Raybould's team runs the numbers and confronts results that are staggering in their brutality. They need shelter for 2 million personnel across hundreds of islands and forward operating bases scattered throughout the Pacific theater. 2 million human beings who need weather protection immediately. At conventional construction rates, the war would be over, won, or lost before half the troops had roofs over their heads. The reality on the ground tells an even darker story that raw numbers cannot fully capture. Soldiers are writing letters home describing how they wake up with boots full of rainwater, how fungus grows on their uniforms overnight like some grotesque science experiment, how temporary tents collapse during storms and send exhausted men scrambling through mud at 3 in the morning. The medical corps submits reports showing that respiratory infections are hospitalizing more personnel than actual enemy action in several sectors. This is not about comfort or maintaining morale. This is about keeping a fighting force functional, about preventing your own troops from deteriorating before they ever encounter the enemy. Think about surviving the voyage across the Pacific, making it through submarine wolf packs and air raids, hitting the beach under fire, and establishing a defensive perimeter, only to spend the next 3 months slowly dying because your shelter is actively destroying your health. Pneumonia spreads through damp canvas. Fungal infections thrive in conditions that never fully dry. Heat exhaustion compounds when there's nowhere to escape the relentless tropical sun. The call goes out to American engineering firms, university research departments, and the Navy's own construction. Battalions. The specifications sound like pure science fiction, a wish list so ambitious it borders on fantasy. Design a building that weighs less than a Jeep but provides shelter for 30 men. Make it fit on a single standard railcar for efficient shipping. Eliminate all foundation requirements so it can be erected directly on sand, coral, or bare volcanic rock. Assemble the entire structure in 1 day using only basic hand tools that any exhausted soldier can operate without specialized training. Keep the total cost under $1,000 per unit. Oh, and manufacture 10,000 complete units ready for immediate shipping within 6 months. And ensure they survive conditions that regularly destroy permanent buildings constructed by professional contractors using conventional methods. It is February 1942, and somewhere in Rhode Island, a small team of engineers is about to transform this architectural impossibility into functioning reality. The Nissen hut blueprint arrives at the Navy's Bureau of Yards and Docks through a peculiar twist of wartime cooperation. British engineers, grateful for American supply shipments keeping their war effort alive, share detailed technical drawings of their World War I shelter design with specifications that tell the story of engineering from another era. 16 feet wide, semicircular tunnels constructed from corrugated iron sheets bolted to wooden internal frames. Simple in basic concept, combat-proven across multiple theaters, and fatally flawed for Pacific deployment in ways that become glaringly obvious under close examination. Commander John Philip Drosfeld studies the British specifications with growing recognition of both brilliant engineering and catastrophic design problems existing simultaneously in the same structure. The genius reveals itself immediately and elegantly. The arch shape naturally deflects wind and sheds water without requiring complex engineering or elaborate support systems. Wind strikes a curved surface and flows over and around instead of slamming directly into a flat wall with maximum destructive force. Rain runs off a semicircular roof without pooling or creating drainage problems. It represents physics working for you instead of against you, the kind of fundamental principle that makes you question why anyone builds. Rectangular structures in hurricane-prone regions, but the problems emerge as an extensive laundry list that would doom this design in Pacific conditions before the first unit even ships to a combat zone. The British huts weigh 3 tons when fully disassembled, which means you need heavy lifting equipment just to move individual components around a construction site. Try loading 3 tons of steel panels onto landing craft while under enemy fire and see how long you survive. The design requires foundation bolts drilled deep into concrete, which demands time, skilled labor, and construction materials that do not exist on islands that are essentially piles of coral debris and volcanic rock. Then there is the wooden internal frame that becomes an all-you-can-eat buffet for termites in tropical climates. Drosfeld circles the ventilation specifications in red ink and underlines them twice for emphasis. 2 small windows, designed for Scottish weather, would transform these shelters into ovens at Guadalcanal's 98-degree average temperature, with humidity levels that make simply breathing feel like drowning. Men would cook inside their own shelter faster than they would under the direct jungle sun. The British learned this brutal lesson through experience in Burma and Singapore, where their Nissen huts became uninhabitable death traps during daylight hours. But another American voice enters this conversation from an unexpected corner of the architectural world. Buckminster Fuller has been preaching prefabricated housing concepts since the 1920s, though most establishment architects dismiss him as an eccentric crank promoting impractical fantasy ideas. His Dymaxion house concept sounds genuinely crazy on the surface. Factory-built structures using lightweight materials, assembled on site like manufactured products, rather than constructed using traditional building methods. In 1942, Fuller's ideas about mass-producing housing, the same way Ford mass-produces automobiles, using industrial materials instead of traditional lumber, and designing specifically for rapid deployment rather than permanent installation, suddenly sound significantly less crazy when your country needs to construct an entire city's worth of shelter every single month. The military has not directly consulted Fuller or incorporated his work into official planning, but his published papers circulate through engineering departments, and his core philosophical insight proves invaluable in ways he probably never imagined when writing them. Treat buildings like manufactured products, not traditional construction projects. Stop thinking like conventional architects and start thinking like industrial production engineers. The Navy consolidates this evolving thinking at their facility in Quonset Point, Rhode Island, a freshly commissioned air station located on Narragansett Bay that most Americans have never heard of and cannot find on a map. The location is not selected randomly or chosen for convenience. Rhode Island possesses deep manufacturing expertise in precision sheet metal work from its jewelry and silverware industries, the kind of exacting metalwork that translates directly to manufacturing building panels with tight tolerances. The state also offers proximity to major steel mills in Pennsylvania and established shipyards that understand marine-grade corrosion resistance better than anyone else in the country. In March 1942, the Navy assembles an unusual team representing a collision of different professional worlds and specialized expertise. Structural engineers from the Strand Steel Corporation, who have spent years building prefabricated farm buildings. Architects from George A. Fuller Construction Company, who specialize in rapid assembly methods and modular construction. Navy officers who have actually served extended tours in the Pacific theater and know what typhoon-proof really means in practice versus what it means on paper in a comfortable stateside office. The team lead, Otto Brandenberger, brings farm building experience that turns out to be precisely right for this seemingly impossible problem. His strand steel agricultural barns use self-supporting arched panels requiring no internal frame whatsoever, which means no wood for termites to devour and no complex joinery to fail catastrophically during violent storms. Farm buildings face their own set of extreme environmental conditions: Midwest tornadoes with devastating wind speeds, massive snow loads that collapse weaker structures, temperature swings ranging from well below zero to over 100 degrees, and the expectation of decades of continuous use. With absolutely minimal maintenance, Brandenberger's radical proposal violates every piece of conventional architectural wisdom accepted as gospel truth in 1942. Eliminate the Nissen hut's wooden skeleton entirely and engineer the corrugated steel skin itself to carry all structural loads. This represents pure heresy in an era where steel is reserved for bridges and skyscrapers, not self-supporting building envelopes. Architects and structural engineers have invested decades developing and refining the principle that you need a strong internal frame to support an external protective skin, exactly the way your skeleton supports your body's soft tissue. But Brandenberger knows something the conventional wisdom has not yet discovered. His agricultural barns have survived direct hits from Midwest tornadoes without any internal framing whatsoever, and he is willing to stake his professional reputation on the bet that this same fundamental principle scales up successfully to military shelter applications. The arch shape itself provides all necessary structural strength if you engineer the geometry and materials correctly. Every individual panel supports every other panel in a continuous curve that distributes loads naturally through the entire structure instead of concentrating dangerous stress at specific vulnerable points. The British contribute another crucial element through their painful experience and hard-won lessons learned across multiple theaters of brutal warfare. Their Nissen huts deployed in Burma and Singapore have taught them exactly how tropical environments systematically destroy buildings in ways that temperate climate engineers never imagine in their worst nightmares. Fungus is not merely cosmetic discoloration that looks unsightly on painted surfaces. It literally consumes wood preservatives and protective paint coatings within months, transforming load-bearing structural elements into crumbling, useless powder. Humidity does not simply make interior spaces damp and uncomfortable for occupants. It aggressively corrodes metal fasteners and connectors until roofs collapse without any warning whatsoever. Insects are not just annoying pests that bite soldiers and cause minor discomfort. Carpenter ants can systematically reduce massive wooden support beams to completely hollow shells in a single breeding season, leaving structures that appear solid from external inspection but contain zero actual load-bearing strength. The detailed British field reports read like genuine horror stories from a nightmare dimension, where buildings possess malevolent life and actively conspire against human occupants. But these reports provide the Quonset development team with something genuinely invaluable: a comprehensive checklist of everything that must be completely engineered out of the final design from day one before the first working prototype gets constructed and tested. No wood can remain in direct contact with ground surfaces where moisture and destructive insects naturally concentrate their activity. All steel components must receive hot dip galvanization treatment, not merely painted surface coating, because conventional paint fails completely in saltwater air within a matter of weeks. Ventilation systems must be aggressive enough to actively prevent interior condensation that literally rains from ceiling surfaces. Every single fastener must remain accessible for field replacement without requiring complete disassembly of the entire shelter structure. By April 1942, the hybrid engineering vision crystallizes into something that might actually function in real-world combat conditions. Take the Nissen hut's genuinely brilliant arch geometry that has already proven itself effective across multiple combat theaters. Systematically strip out everything that makes it excessively heavy, environmentally vulnerable, or dependent on skilled construction labor. Incorporate Fuller's mass production philosophy that treats buildings as factory-manufactured products rather than custom construction projects. Apply American steel manufacturing industrial capacity that can produce standardized components by the thousands per week. Then, meticulously engineer every single design detail specifically for the unique environmental hell of Pacific Island warfare. The result is not merely an incremental improvement on existing military shelter designs. It represents something genuinely revolutionary, born from desperate crisis and impossible deadlines, and the kind of radical innovation that only emerges when conventional failure means young men dying miserably in tropical rain. April 15, 1942. Otto Brandenberger walks into a Quonset Point warehouse accompanied by 30 hand-selected engineers and facing a deadline that would be absolutely laughable if the overall war situation were not so desperately critical. 60 days to complete design work, construct working prototypes, conduct field testing, and secure final approval for a completely new building system that does not yet exist even on paper. The assembled team works in continuous rotating shifts around the clock, sleeping on military cots pushed against warehouse walls, subsisting on Navy mess hall coffee, and the kind of intense pressure that either produces genuine brilliance or triggers complete psychological collapse. Brandenberger divides his engineering crew into specialized functional teams working parallel development tracks. One group tackles complex aerodynamics calculations and structural loading analysis. Another team figures out how to efficiently nest individual components for maximum shipping density. A third works exclusively on solving the joint and fastener problems that plagued the original British design and caused field failures. The first truly radical decision happens on day 3 of the 60-day countdown. Traditional architectural drawings require weeks of careful production time, and the development team simply does not have weeks to spare. Instead, they construct and test in real time using iterative prototyping. Sketch a design detail in the morning, have the metalworking shop fabricate actual components by afternoon, conduct stress testing overnight, and revise based on failure analysis by dawn. This rapid iterative prototyping approach is completely standard engineering practice in 2025, but represents revolutionary methodology in 1942 when buildings are designed completely on paper before a single physical piece gets cut or formed. The warehouse floor rapidly becomes a chaotic laboratory scattered with failed joint experiments, bent and broken test panels, and increasingly refined versions of each critical component. The engineers deliberately steal a proven technique from aircraft manufacturing protocols. Every single part receives a unique identifying number. Every design revision gets thoroughly documented with detailed notes. Nothing advances to the next prototype generation without conclusively solving all failure points identified in the previous version. The final structural dimensions emerge from brutal practicality rather than aesthetic considerations or architectural fashion. 16 feet wide represents the absolute maximum width that fits on a standard American railcar without requiring special permits or custom shipping arrangements. 20 feet long per individual section, short enough that 4 average men can physically lift and maneuver a single panel, but long enough to create genuinely usable interior space when sections connect. 48 feet total length when fully assembled, providing housing capacity for 36 men with stacked bunks, or converting to office space, medical treatment stations, or supply storage facilities. The Quonset development team discovers through extensive testing that this specific size combination hits a genuine sweet spot in structural engineering principles. Make the shelters smaller, and you waste precious shipping capacity moving air instead of usable structure. Make it larger, and individual panels become too heavy for field assembly by exhausted troops, or the arch geometry starts requiring internal support members that reintroduce all the problems they are systematically trying to eliminate. The arch radius calculation alone consumes 2 full weeks of the precious 60-day development deadline. 2 flat and wine forces could peel the entire structure apart like opening a sardine can, with catastrophic results. Too steep and you waste valuable interior headroom while creating difficult end-wall geometry that complicates manufacturing and assembly. Brandenberger's team settles on an 8-foot radius, creating a perfect semicircle that provides 7 feet of usable headroom at the sidewalls and generates what structural engineers call a self-bracing arch configuration. The corrugated steel naturally wants to hold this curved profile, which means individual panels can be significantly thinner and lighter than flat sheets would require for equivalent structural strength. They run extensive load calculations, showing this specific design can theoretically handle snow loads up to 40 pounds per square foot and survive wind speeds exceeding 100 miles per hour. But theoretical engineering calculations and actual Pacific typhoons are completely different animals with vastly different destructive capabilities. By day 40 of the 60-day countdown, they have assembled something that looks like it might actually work under real combat conditions. A Frankenstein's monster of riveted panels, experimental joint designs, and borrowed hardware components. The first complete functional prototype goes up on May 25, 1942, assembled by 6 ordinary sailors who have received exactly 4 hours of basic instruction and access only to standard hand tools. The assembly time totals 14 hours, which is genuinely encouraging progress, but not yet good enough to meet operational requirements. The Navy wants reliable single-day construction capability because marine amphibious landing schedules absolutely do not allow for multi-day building projects on contested beaches. The development team identifies the critical bottleneck immediately: the floor system. They have been attempting to include a wooden floor as part of the basic package, but flooring represents the slowest component to assemble and the first structural element to rot completely in tropical conditions anyway. The solution emerges as elegant in its radical simplicity. Eliminate the floor entirely from the basic shelter design. The hut sits directly on whatever surface currently exists: coral, sand, volcanic dirt, or if you are exceptionally lucky, gravel, for specific applications requiring finished floors. Those can be added later as separate construction projects using local materials. But the basic shelter structure achieves complete weather protection without any floor system whatsoever. This single design decision cuts assembly time to 8 hours and reduces total shipping weight by 1,200 pounds per complete unit. On June 10, 1942, the final approved prototype stands complete and ready for formal evaluation. 96 individual corrugated steel panels, each weighing less than 50 pounds, that bolt together to create 720 square feet of fully enclosed protected space. Total materials cost $1,394. Total shipping weight 9,000 pounds. The real grueling test begins when the Quonset prototype faces what amounts to an engineering interrogation designed to expose any weakness. Navy structural engineers arrive carrying wind load tables, actual typhoon meteorological data from weather stations scattered across the Pacific, and a healthy professional skepticism that this corrugated metal tunnel can possibly survive what nature routinely throws at tropical islands. The numbers they are working with are not theoretical projections or academic estimates. They represent data pulled from actual documented weather events that have already occurred. Typhoon Gloria struck Guam in November 1940 with sustained winds measuring 140 miles per hour and peak gusts reaching 180. The 1935 Labor Day hurricane that tragically took 400 lives in the Florida Keys produced winds so powerful they literally sandblasted paint off buildings and drove wooden planks through palm trees like rifle bullets. If Quonset huts fail catastrophically during a major storm, the result is not merely property damage and insurance claims. It means service members lost and critical military equipment destroyed at the worst possible moment. Brandenberger's engineering team starts with the fundamental physics principles of why the arch shape works so effectively under extreme wind loading. When wind strikes a flat vertical wall, it creates what engineers call a pressure coefficient, pushing directly against the surface with maximum destructive force. But a properly curved surface deflects wind upward and around the structure, reducing that destructive pressure dramatically through simple geometry. Think about how river water flows smoothly around a rounded stone versus slamming violently into a dam wall. The semicircular Quonset profile means hurricane-force winds slide over the structure rather than attempting to punch directly through it with full force. The corrugations running lengthwise add a second layer of structural brilliance to the overall design. Those parallel ridges create structural rigidity using exactly the same principle that folding a flat piece of paper makes it dramatically stronger than leaving it completely flat. Each individual corrugation functions like a miniature I-beam, actively resisting bending. Forces that would crumple smooth sheet metal into useless wreckage. The mathematics become genuinely fascinating when you examine in detail how loads distribute through the complete arch structure. In a conventional rectangular building, the roof pushes downward on load-bearing walls, the walls push downward on foundation systems, and everything depends on those vertical load paths remaining intact, under stress. Storm winds can literally lift entire roofs off buildings because they represent separate structural elements merely sitting on top of walls. The Quonset arch changes this loading pattern completely. It forms a single continuous curve where every panel shares structural loads with its immediate neighbors through direct mechanical connection. Engineers call this a compression ring, and it operates on the same fundamental principle that keeps ancient stone bridges standing for centuries without any mortar whatsoever. The hoop stress, representing tension trying to spread the arch apart at its base, gets resolved by the ground itself, providing passive resistance. Each Quonset panel bolts to adjacent panels with 3/4-inch steel bolts spaced every 6 inches, creating what is essentially a 48-foot-long steel cable wrapped in an arch configuration. But theoretical structural strength calculations mean absolutely nothing without rigorous real-world testing under actual conditions. So the Navy sets up validation experiments that border on genuinely sadistic treatment of the prototype. They construct a full-scale Quonset hut at Davisville, Rhode Island, and instrument it extensively with strain gauges, pressure sensors, and deflection meters measuring structural response. Then, they wait patiently for the first major nor'easter storm to arrive. On March 3, 1943, a massive storm system hits with 75-mile-per-hour winds and heavy snow loading, creating perfect test conditions. The instruments record the structure flexing by less than 2 inches at the crown peak, then returning completely to its original shape when wind forces subside. The panel joints hold perfectly. Nothing leaks through the connections. The structure behaves exactly as the theoretical calculations predicted, which is simultaneously thrilling and slightly terrifying because it means they are about to bet thousands of young lives on this untested design. The tropical environment testing proves significantly more challenging than wind load validation. You simply cannot simulate years of jungle exposure conditions in a Rhode Island warehouse over a few weeks. So the Navy ships a complete test unit to the Panama Canal Zone, where humidity averages 85% year-round and temperatures stay consistently above 80 degrees. 6 months later, the detailed field report comes back with mixed results. Minimal corrosion damage on properly galvanized panels, no structural degradation, but serious operational problems with interior condensation. When hot, humid air contacts the relatively cooler steel surfaces at night, water literally rains from the ceiling inside the hut, creating miserable conditions for occupants. The engineering solution requires adding ventilation louvers at both end walls and along the ridgeline, creating openings that allow hot air to escape and establish continuous airflow without compromising structural strength or weather protection. These ventilation additions increase unit cost by $47, but completely transform the hut from an uninhabitable steel sauna into something human beings can actually occupy in tropical heat. The final significant engineering challenge addresses the foundation question that plagued the original British design. How do you properly anchor a 9,000-pound building to loose sand or coral without pouring concrete foundations? The answer comes from tent technology, principles scaled up to building applications, steel stakes driven into the ground connected to the hut's base with adjustable tension cables. For harder surfaces, the team designs a bolt pattern allowing the hut to mount directly to wooden sleepers or pierced steel planking. The beauty of this system lies in its forgiveness and flexibility. The structure can flex slightly with ground movement without tearing itself apart catastrophically. June 1942. The War Production Board officially approves Quonset hut manufacturing for immediate large-scale production, and what happens next represents American industrial capacity operating at its absolute wartime peak. The Navy contracts with 10 major steel fabricators scattered across the Midwest and Northeast, companies that were manufacturing grain silos and water storage tanks 6 months ago and are now rapidly retooling entire facilities for military shelter production. The Strand Steel Corporation converts its entire Penrose facility outside Philadelphia to exclusive Quonset production running 3 shifts. George A. Fuller Construction takes over a former automobile parts manufacturing plant in Chicago and begins immediate conversion. Great Lakes Steel dedicates 2 complete rolling mills to nothing but corrugated panel production for military applications. By August, these factories are collectively producing 1,500 complete huts per week, and the production numbers keep climbing steadily. The manufacturing process borrows heavily from proven automotive assembly line logic developed and refined by Ford. Massive steel coils arrive by rail freight. Each coil measures 4 feet wide and contains sufficient steel to produce 30 finished panels. Industrial rolling machines corrugate the flat steel sheets, creating those structural ridges at precisely 2.67 inches on center spacing. The corrugating process work hardens the steel through mechanical deformation, making it significantly stronger than the original flat sheet that entered the machine. Next, the formed panels travel through galvanizing tanks where they get dipped in molten zinc, heated to 850 degrees Fahrenheit. This zinc coating is not merely decorative paint, it forms a metallurgical bond that sacrifices itself to corrosion before the underlying steel can rust. In Pacific saltwater air, this galvanizing treatment means the critical difference between a 5-year lifespan and a 50-year lifespan. The galvanizing process adds an extra $112 to per unit cost, but proves absolutely non-negotiable after field reports show ungalvanized steel corroding completely through in just 8 months. Each complete hut kit gets packaged with obsessive attention to shipping logistics and transport efficiency. The 96 corrugated panels nest inside each other like stacked bowls, reducing the package height from 8 feet down to just 14 inches. The end walls, plywood sheets with pre-cut door and window openings, pack flat between the steel panels. All fasteners, bolts, washers, and hardware get boxed in a single wooden crate that includes illustrated assembly instructions designed for men who might not read English fluently. The entire complete kit loads onto one standard flatbed railcar measuring 40 feet long. This packaging density proves absolutely crucial, because every train heading to West Coast ports is carrying either Quonset huts, ammunition, food supplies, or military vehicles. There is zero room for inefficient cargo or wasted shipping capacity. The shipping choreography becomes genuinely wild in its complexity and scale. Trains leave Philadelphia and Chicago daily, arriving at San Francisco, San Diego, and Seattle, where Liberty ships and specialized cargo vessels wait at dock for immediate loading. Longshoremen load complete huts into ship holds using the same crane systems originally designed for moving tanks and heavy artillery. A single Liberty ship can carry 200 complete Quonset huts, plus their assembly hardware, representing shelter capacity for 7,200 men. The War Shipping Administration tracks every cargo manifest meticulously because these are not merely buildings or construction materials. They represent critical strategic assets directly impacting combat capability. A hut that ships to Guadalcanal in September might house a bomber crew by October, making the tangible difference between operational aircraft and pilots sleeping miserably in contaminated mud. The assembly process on the receiving end is where Quonset design genius really shines in practical application. The Navy's construction battalions, the famous Seabees, develop standardized procedures that transform shelter erection into a precisely choreographed military operation. 6-man crew, 8 hours, 1 complete hut ready for immediate occupation. The process starts with basic site preparation. Level the ground surface, remove vegetation, lay down a gravel base if materials are available. 2 men handle the end walls, while 4 crew members wrestle the steel panels into position. The panels overlap by 6 inches and bolt together with those 3/4-inch fasteners. No welding equipment required, no concrete needed, no skilled trades necessary, just standard wrenches, a level, and men who follow the illustrated instructions carefully. The official speed record gets set on Espiritu Santo in January 1943 when a specially trained Seabee crew erects a complete hut in 4 hours and 17 minutes. But that represents showboating for the record books. The real sustained achievement is continuous production across hundreds of islands where crews assemble 5 or 6 complete huts per day, day after day, building entire forward bases faster than Japanese bombers can destroy them. By December 1943, monthly production hits 8,000 units, and the logistics network moves so efficiently that huts ordered in Pennsylvania reach New Guinea within 40 days total transit time, including ocean crossing and trans-Pacific transport. The cost accounting tells the ultimate victory. Story in stark numbers. Each Quonset hut provides 36 men with weatherproof shelter for $1,394 in materials and approximately 60 man-hours of assembly labor. Compare this to conventional barracks construction. $12,000 in materials, 400 man-hours of skilled carpentry labor, and 6 weeks total construction time. The Quonset delivers equivalent shelter at 1/10 the cost in 1/20th the time. By mid-1944, the U.S. military has deployed over 160,000 units to every combat theater. That represents housing capacity for nearly 6 million personnel built in less than 2 years. Guadalcanal, August 1942. The first combat-deployed Quonset huts arrive. On a beach where the temperature hovers at 95 degrees with 90% humidity, and Japanese bombers make daily visits attempting to crater anything resembling American infrastructure. Marine engineers unload the flat-packed steel panels under sporadic artillery fire and start bolting them together in a coconut grove, still showing fresh scorch marks from the previous week's shelling. Within 12 hours, Henderson Field has 10 new structures, housing exhausted maintenance crews for the battered F-4F Wildcats operating from the makeshift airstrip. The real brutal test comes 3 days later, when a Japanese bombing run scores a near miss. A 500-pound bomb detonates 40 yards from a hut packed with aviation mechanics. The massive blast wave flattens. Surrounding palm trees and shreds canvas tents like tissue paper, but the Quonset flexes under the shock wave. Dirt and shrapnel rattle off the corrugated steel like hail. When the smoke finally clears, the structure stands intact with every man inside, shaken but alive and functional. The unforgiving jungle environment proves as hostile as direct enemy action. Within 2 weeks, red rust streaks appear on any ungalvanized fasteners. The corrosive saltwater air eats through standard hardware like acid. Fungus grows on everything that holds moisture, turning the inside surfaces into abstract art exhibits of black and green mold. The ventilation louvers that seemed adequate in Rhode Island testing barely move the suffocating air. Marines start propping doors open 24 hours and cutting additional vent holes with tin snips, technically violating structural specifications, but making the huts actually livable. These field modifications get carefully documented and sent back to Quonset Point, where engineers immediately incorporate them into later production runs. More ventilation openings, larger louvers, and every single fastener galvanized regardless of location or function. Iwo Jima, February 1945. The volcanic island offers a completely different kind of environmental hell. Black volcanic sand that blows into every crevice and mechanical joint, no topsoil whatsoever for grounding stakes, and the constant threat of artillery from Mount Suribachi dominating the island. Seabees arrive on D-Day +2 and start assembling Quonset huts. Literally under fire, bolting panels together while mortar rounds impact 200 yards away. The volcanic sand proves impossible for traditional stake anchoring methods, so crews improvise on the spot by filling empty oil drums with sand and running cables connecting drums to the hut bases. When a Pacific typhoon hits in March with 110-mile-per-hour winds, those improvised anchors hold perfectly while wooden structures across the entire island disintegrate. The base commanders report back to Pearl Harbor as succinct and powerful. Quonset huts survived, everything else gone. The Arctic environment tests the design from the opposite extreme end of the climate spectrum. Alaska's Aleutian Islands campaign sees Quonset huts deployed at Dutch Harbor and Adak, where temperatures plunge to -40 degrees and winds regularly exceed 100 miles per hour. The extreme cold makes the steel brittle, and early units suffer from panels cracking at the bolt holes under thermal stress. Engineers respond by specifying cold-rolled steel with different metallurgy specifically for Arctic deployments and adding rubber gaskets at every joint to maintain flexibility. Heating the huts creates its own set of problems. Warm interior air meeting frozen steel produces condensation that literally rains inside until crews learn to install insulation blankets and run continuous ventilation even in sub-zero weather. By winter 1943, weatherized Quonset models include internal insulation batting, double wall construction for extreme cold zones, and modified ventilation systems that prevent heat loss while managing moisture. North Africa and Italy bring entirely different challenges. At Palermo, Sicily, a Quonset hut pressed into emergency service as an ammunition depot takes a direct hit from a German 88mm artillery shell. The shell penetrates the steel skin, detonates inside among crates of small arms ammunition, and the resulting explosion should theoretically vaporize the structure completely. Instead, the arched shape channels the blast force outward through the walls and roof in a pattern that leaves the structural frame twisted but standing. EOD crews examining the wreckage note that a rectangular building would have collapsed completely, trapping anyone nearby under tons of rubble. The arch's inherent strength, that compression ring effect, means even catastrophic damage does not trigger total structural failure. The Pacific typhoon season of 1944 delivers the ultimate stress test. Super Typhoon Cobra hits the Philippines in December with winds measured at 140 miles per hour and a 20-foot storm surge. At Tacloban, the storm destroys 80% of all structures on the base. Wooden buildings explode into splinters. Concrete block structures collapse when wind undermines their foundations. But of 43 Quonset huts on the base, 39 survive completely intact and 4 suffer repairable damage consisting of bent panels and torn seams, but no total failures. Engineers analyzing the survivors find that proper anchoring matters more than any other single factor. Huts with adequate ground attachment ride out the storm. Those with improvised or insufficient anchoring roll like tumbleweeds. May 8, 1945, victory in Europe. August 15, 1945, victory over Japan. Suddenly, the United States military owns roughly 170,000 Quonset huts scattered across 6 continents and has absolutely no clear idea what to do with them. The original strategic plan assumed these were temporary wartime expedients that would be scrapped or abandoned once permanent facilities could be constructed. But something completely unexpected happens. Nobody actually wants to get rid of them. At hundreds of military bases slated for closure or downsizing, base commanders look at their Quonset huts and see not obsolete wartime relics, but perfectly functional buildings that cost nothing to maintain and can be repurposed for virtually anything. The War Assets Administration, tasked with liquidating surplus military property, finds itself facing an unusual problem. There is significantly more demand for used Quonset huts than they have available inventory to sell. Veterans returning home discover a housing shortage so severe that families are living in converted chicken coops and sharing tiny apartments with 3 other families. The construction industry, starved of materials and skilled labor during 4 years of total war, cannot build fast enough to meet explosive demand. Into this desperate crisis steps the Quonset hut, now available for civilian purchase at liquidation prices ranging from $1,000 to $2,500 for a complete structure that would cost $8,000 to build conventionally, if you could even find contractors available to build it. The federal government actively encourages this repurposing through programs that prioritize veterans for Quonset purchases and financing. By late 1946, suburban developments made entirely of converted Quonset huts spring up around every major American city. Roger Young Village in Los Angeles houses 750 families in converted military huts. Vetville developments appear near universities where the GI Bill is flooding campuses with students who need immediate affordable housing. The architectural adaptation gets genuinely creative, remarkably fast. Families add wooden facades to the curved ends, making the structures look less like military surplus and more like quirky cottages with character. Interior walls divide the open space into separate bedrooms, living areas, and functional kitchens. Windows get cut into the steel sides, technically violating every structural principle, but making the spaces actually livable for family life. Some ambitious owners go further, burying the entire structure halfway into the ground for earth-sheltered insulation or connecting multiple huts end-to-end to create sprawling compound homes. Housing inspectors and building code officials initially balk at approving these radical modifications. But the housing shortage is so desperately acute that municipalities reluctantly grant permits rather than leave families homeless. In Portland, Oregon, an entire neighborhood called Fairview Edition consists of 350 Quonset homes. Residents plant gardens, paint their steel walls cheerful colors, and build conventional-looking porches that disguise the utilitarian military origins. Churches discover Quonset huts solve a completely different problem, providing worship space for exploding suburban populations without the decade-long capital campaigns traditional church buildings require. First Presbyterian Church of Levittown, Pennsylvania, holds regular services in a Quonset hut from 1952 until 1967, when they finally raise sufficient funds for a conventional sanctuary. Dozens of congregations make the same practical calculation. $2,500 for immediate usable space beats $150,000 for eventual architectural grandeur. The acoustics are admittedly terrible, the aesthetics underwhelming, but people can gather for worship next month instead of next decade. Some of these temporary church huts remain in continuous service for 30 years, outlasting the generations who first considered them stopgap solutions. Education sees similar widespread adoption. Post-war school enrollment explodes as the baby boom hits, and school districts face the same impossible mathematics that plagued the military in 1942. They need classroom space immediately, and conventionally built schools take years to design and construct. Rural districts especially embrace Quonset classrooms. A single hut provides space for 30 students at 1/10 the cost of traditional school construction. By 1950, an estimated 3,000 schools across the United States include at least one Quonset hut classroom. Some students spend their entire elementary education in these steel tunnels, learning multiplication tables and history lessons under curved ceilings that once sheltered B-29 crews in the Pacific. The commercial sector enthusiastically joins the adoption party. Small businesses, machine shops, auto repair garages, warehouses, farm equipment storage operations recognize that Quonset huts deliver clear-span space without internal support columns, making them absolutely perfect for industrial work. A welder can set up a complete shop in a surplus hut for less than 2 months' rent in conventional commercial space. Agricultural use proves especially popular and widespread. The original Strand Steel Corporation, having helped design military Quonsets, returns to manufacturing civilian versions specifically marketed to farmers and ranchers. Thousands of Midwestern farms add Quonset storage buildings for grain, equipment, and livestock shelter. The maintenance requirements are refreshingly minimal. Hose off the exterior once a year, check the bolts occasionally, and the structure lasts indefinitely. Modern disaster zones tell you everything about why the Quonset hut's engineering DNA keeps reappearing in 21st century emergency response. When the 2010 Haiti earthquake destroys Port-au-Prince, relief organizations face the same fundamental equation American military planners confronted in 1942. Immediate shelter for hundreds of thousands of displaced people, no existing infrastructure, no time for conventional construction, and environmental conditions that destroy inadequate temporary housing within months. The solution that emerges borrows directly from Quonset principles, even when contemporary designers do not consciously realize they are channeling 1940s military engineering. arched steel frames, corrugated metal panels, prefabricated components that ship flat and assemble quickly. The basic formula has not changed because the underlying physics and logistics have not changed one bit. The United Nations High Commissioner for Refugees currently uses shelter systems called RHUs, refugee housing units, that are essentially Quonset huts incorporating 80 years of material science improvements. Instead of corrugated steel, they use insulated composite panels. Instead of bolt-together assembly, they employ snap-fit connections. But the core concept remains absolutely identical. Curved profile for structural efficiency and wind resistance, self-supporting arch, eliminating internal framing, flat-pack shipping allowing massive quantities to reach remote locations, and assembly by unskilled labor with minimal tools. A two-person crew can erect a modern RHU in 4 hours, almost exactly matching the 1942 Quonset specifications. These units currently house over 200,000 displaced persons in refugee camps across Africa, the Middle East, and Asia. Hurricane-resistant construction has rediscovered arch geometry after decades of building conventional rectangular structures that hurricanes repeatedly destroy with monotonous regularity. After Hurricane Katrina devastated the Gulf Coast in 2005, engineers studying which buildings survived found that curved structures consistently outperformed rectangular ones by dramatic margins. The Mississippi coast saw entire neighborhoods of conventional homes reduced to bare foundation slabs, while a handful of Quonset-style metal buildings stood intact with only minor damage. This empirical evidence triggered serious research into what structural engineers now call aerodynamic architecture, designing buildings that work with wind forces rather than resisting them through brute strength. The result looks remarkably like a Quonset hut because the fundamental physics have not changed. Wind flowing over a curve creates significantly less destructive pressure than wind slamming into a flat surface. Today, exactly as it did in 1942, the modern tiny house movement unknowingly reinvents Quonset principles when designers seek maximum interior space with minimum materials and cost. Several companies now manufacture arch-roofed prefab cabins using the same corrugated metal and self-supporting curve that Otto Brandenberger pioneered 8 decades ago. These sell to buyers seeking affordable housing, disaster-resilient structures, or off-grid living solutions. The marketing emphasizes sustainability and modern design aesthetics, rarely mentioning that the fundamental architecture is a World War II military shelter. Some high-end architectural firms have completely rehabilitated the aesthetic, designing luxury versions with floor-to-ceiling glass end walls and premium finishes that cost $300 per square foot while maintaining the signature curved profile. The arch has evolved from utilitarian necessity to deliberate design statement. Military applications never actually stopped using the basic concept. The U.S. Armed Forces still deploy arch-style shelters in conflict zones. Afghanistan, Iraq, and classified locations all feature modern descendants of the original Quonset. Current military specifications call for units that can be helicopter lifted to remote mountain bases, assembled in active combat conditions, and survive IED blast waves. The materials have dramatically evolved: aluminum alloy frames, Kevlar reinforced panels, integrated climate control systems. But if you showed a 2025 military deployable shelter to the 1942 Quonset Point engineering team, they would immediately recognize their own fundamental design philosophy executed with better materials. The most recent innovation involves expandable versions that deploy from standard shipping containers, unfold like complex origami, and lock into rigid arch structures within an hour. The economic argument that originally justified Quonset huts in 1942 remains equally compelling today. When disaster strikes or rapid deployment is operationally required, conventional construction simply cannot compete on speed or cost. A modern engineered arch shelter delivers complete weather protection for approximately $50 per square foot, including shipping and field assembly. Conventional construction in the same challenging locations, assuming contractors are even available, costs $150 to $300 per square foot and requires months instead of days. For humanitarian organizations operating on limited donor funding or military logistics, managers handling trillion-dollar budgets, this cost differential matters enormously. The fundamental mathematics that drove Quonset development, how do you shelter the maximum number of people for the minimum cost in the shortest possible time, has not changed because scarcity economics have not changed. Perhaps the ultimate validation comes from space exploration, where NASA and private space companies designing Mars habitats keep independently arriving at Quonset-like solutions. Proposed Martian shelters feature arched profiles to resist the planet's severe dust storms, prefabricated components that ship aboard spacecraft with extreme weight restrictions, and self-supporting structures that do not require extensive foundation work in Martian regolith. The constraints of interplanetary construction, extreme environmental conditions, minimal available tools, unskilled assembly, maximum strength from minimum materials, mirror the Pacific Theater challenges of 1942 so precisely that engineers independently rediscover the same fundamental solutions. When humans finally build permanent shelters on another planet, there's a genuinely reasonable chance those structures will owe their design heritage to 30 engineers working in a Rhode Island warehouse during the darkest days of World War II, solving an impossible problem with corrugated steel and brilliant simplicity that transcends generations and planets.